Here we go. The Maclaurin series. Okay. This is where we like I said in our last lesson, we are getting now to like the applications that involve both derivatives and integration. And Maclaurin series is another one of those. So we're going to learn how to approximate a function using the Maclaurin series. So a power series can either be added, multiplied, subtracted. All the basic operations could be differentiated, and it can be integrated just like ordinary polynomials. Okay. In this course, we consider a special case of the Taylor series where a is equal to 0. So what you see that's printed, that is the Taylor series. You do not have to be responsible for that. But essentially, when a, or actually in this case, it's going to be C because it's the only version I could find on the internet. That was all nice and pretty. Whenever C is equal to 0, that is called the Maclaurin series. So you're only considering it for that one situation, okay? When it's equal to 0. This is the Maclaurin series. This is what you're going to need to be able to work with. But essentially, it is the sum when k equals 0 all the way up to infinity of your function to the k power when your x value is 0 over k factorial times x to the k power. Now, do realize that k is essentially a certain number of terms that you're going to be adding in your particular series. In some of the examples that I've seen, you're probably looking at the first 3 terms of the series or the first 4 terms of the series. So k would essentially go all the way up to 4, and that would like be the top of your summation. Okay. So for any values of x where the series converges, remember converging means we're going to a particular number when we add all the terms up together, is an exact representation of the function. That's what the Maclaurin series shows us. However, if we just consider the first n terms of the Maclaurin series expansion, which is what you guys do for this course, we are left with an nth order polynomial approximation for the function. So in other words, when you add up the first 4 terms or the first 3 terms in a Maclaurin series, then you're able to approximate it pretty much similar like you would if it was a polynomial function. And so this right here is essentially the formula from the other page, simplified down to a particular number of terms that you'll be adding. So let's do this. We're going to find the Maclaurin series representation for f of x equals 1 over 2 plus x. Okay. Find the Maclaurin series for the representation for 1 over 2 plus x. So just to refresh your memory, went ahead and pulled the Maclaurin series from the other page here, just so I can make sure that I don't have to keep flipping back and forth. One thing I do want to do is I don't want to work with this as a fraction. So how can I rewrite this so it's no longer a fraction? Very good. And I definitely want to make sure that I do this because if you look at the Maclaurin series, what does that f prime mean? I need the derivative, and I'd rather have it as a power versus as quotient rule. You see what I mean? I'm also going to need the second derivative, the third derivative, et cetera, et cetera. So let's go ahead and let's pull out the first derivative of my function. Y'all remember how to do this? It'd be to the negative second power, yes. Remember, with derivatives, you bring down the exponent. With respect to the inside, you subtract 1 from your exponent, then you multiply by the derivative of the inside, old school chain rule. The derivative of the inside is just 1. Luckily, so then our first derivative is just negative 1, 2 plus x to the negative second power. I am leaving it like this for a reason. Well, 1, I got to do the second derivative, and I got to do the third derivative, okay? If I leave it like this, we're going to essentially see some patterns. So my derivative of my first derivative, I repeat the same process, right? I bring down the exponent. So that's going to become -1 times -2, 2 plus x to the negative third power, and then I will multiply by the derivative of the inside, which is again just 1. The third derivative, it's going to be what? Then 2 plus x to the negative fourth power, and realize that, you know, plus ... means that we're continuing indefinitely repeating this process, which means it's starting to form a pattern. Starting to form a pattern. If I were to keep going, in general, what would the nth derivative be? This is what we're going to have to try to. So in general, we have this formula after a little bit of talking off camera. We have -1 to the nth power times n factorial times 2 plus x to the negative parenthesis n plus 1. Remember, when we're alternating between the numbers being positive and negative, that's where the -1 to the nth power comes from. N is representing our particular derivative that we're on. The factorial, because we are noticing that we're essentially increasing our number. 1 times 2 times 3, the next one would have been times 4, the next one would have been times 5, so that's a factorial representation. And our exponents are continuing to increase, but the number is staying negative. So now that we have that, we are able to find the Maclaurin series representation, okay? Which is essentially this down here that we can represent it as a sum. So we need to find what f to the kth power, which is essentially what we've used as n. K is n, so don't let that throw you off. K is n. We need to find it to the 0 power. So I am going to replace n with k just so I can fit the formula. I'm going to replace x with 0. When I do that, that becomes -1 to the k power times k factorial times 2 plus 0, because I'm plugging in 0 for x, to the negative k plus 1 power. This is what I have. So I'm going to have the sum of k equals 0 to infinity. Yep. I take a moment to make sure everything was going good. -1 to the k power, k factorial to negative k plus 1. So that right there, what I've written so far in the pink, just represents what I've boxed in purple in my formula. I divide it by k factorial, and then I multiply it by x to the k power. Do you notice anything? Yeah, What were you going to say? It does, because the k factorial was being multiplied to the other two terms up there. So now I have the sum, k equals 0 to infinity. You see, I got a negative exponent there. How do I make it positive? So that becomes my denominator. So I have 2 to the negative. Nope, it's not negative anymore. Be 2 to the regular k plus 1 power. I have a -1 to the k power at the top still, and I'm being multiplied by x to the k power. And that is the Maclaurin series representation for this particular function. It's a tad bit different, but let's keep going. Now, that was the part A. This is the part B. We're going to use what we just found, and we're going to find capital M sub 4 of x, which is known as the fourth order Maclaurin polynomial approximation for 1 over 2 plus x. Once we have that polynomial approximation, then we're going to compare the fourth order Maclaurin value when x is equal to 1, and we're going to compare it with f of 1. So to find the fourth order, essentially what we're doing now is we are replacing our k value with 4. Real quick, I'm just going to go back. It's right here. Okay. Now we're essentially replacing our infinity with the value of n in our formula. Okay, so you guys already have it written down from before. It's what I wrote in black here. I'm replacing infinity with 4 since I'm now going to the fourth order, and I'm replacing all of my and then I'm going to do the sum from 0 to 4. So let me copy this over. Was it k plus 1? Thank you. All right. So now we have to do the sum from 0 to 4. That means I'm going to plug in 0 for k, going to plug in 1 for k, 2 for k, 3 for k, 4 for k, add them up. And then I'm going to get my polynomial approximation that way. So here we go. It's -1 to the 0 power, 2 to the first power, x to the 0 power. So all I literally did was replace k with 0 through 4. And now I'm going to simplify. Of course, anything to the 0 power is. So this first term is going to be 1/2. My second term is going to be a -1/4 x. My next term is going to be a positive 1/8 x to the second. My next term is going to be -1/16 x to the third. And my last term is going to be 1/32 x to the fourth. And that is my fourth order Maclaurin polynomial approximation. Exactly. And so now I can take this and I can compare the fourth order when x is 1 with f of 1. And let's see what actually happens. Well, first off, f of 1 we can get by just plugging into the function, which is what? 1/3. Okay, but we're essentially showing the sum as we go, as we're adding terms technically to infinity. Okay, it should converge to a particular number. So when I plug in 1, I get 1/4 minus 1/4 plus 1/8 minus 1/16 plus 1/32. What is the sum of that? What's the common denominator? 32. So this becomes 16 minus 8 plus 4 minus 2 plus 1. What does that add up to equal? So this turns into 11/32. What? Yeah, you added the one. 11/32 and 1/3. They are different, but in actuality, it is really close. Because 11/32 is really close to 11/33, which is what? It's 1/3, right? It's just 1 away. If I kept adding terms, if I went to the 5th order, maybe the 6th order or 7th order, it would have been something that's even closer to 1/3. So that's how we can use the Maclaurin series to help us find an approximation and, of course, find converging values. All right, let's look at this next example. So it's a little bit different. We're looking at the function e to the x. We're looking at the function e to the x. Okay? So we're going to find the nth derivative, f to the n power of x. Of course, we're only going to look at when n are positive. What does z mean? True, but what does the z mean? Integers. So I'm looking at the positive whole numbers. So first derivative, second derivative, third derivative. But this is e to the x. What's the derivative of e to the x? It's the second derivative of e to the x. And the third. So the nth derivative is just what? E to the x. So when it says, hence explain why e to the x equals that particular summation, which essentially equates to that, of course, we're not going to use that to explain it in words. We're going to use the formula to show how we get to that point. Okay? And showing the formula is the same thing that we did on the previous slide. Okay? Same thing we did on the previous slide. So even though it doesn't say use the Maclaurin series to explain this, you need to be able to recognize that this is the same notation as it. So if you were to get something like this in the IB exam, it's essentially saying use the Maclaurin series to explain why it is this particular summation here. So you know the formula to be the sum when k equals 0 to infinity of -1 to the k power, f to the k power of 0. Help me out, y'all wrote this down. X to the k. There was nothing else in the numerator? Okay, cool. So then that means we need to figure out what f to the k power of 0 is. So that means it is 1. That means we actually have to plug in the 0 power into e to the x, which we know is equal to 1. So then that becomes the sum. No, we are missing something. No, never mind. You're all right. I'm sorry. So this becomes 1 over k factorial times x to the k, which is what you see there. Now, granted, this is e to the x, okay? Of course, the proof would be just as simple as that, okay? We know that f, the breakdown of it goes f of 0 plus f prime of 1, or x times f prime of 0. Then it becomes x squared over 2 factorial f double prime of 0, and so on and so forth. We know that f of 0 is 1. F prime of 0 is going to be 1. F double prime of 0 is going to be 1. And 2 factorial is just 2. And so that is how we get exactly what we see on our board. Use the formula to get the simplified version of the Maclaurin series. So use that formula, simplify to get that, showing the plugging in of 0 to get 1, plugging in 1 into the formula to get the summation. The first 2 Maclaurin polynomial approximations for e to the x are given to us. The first one is 1 plus x. The second one is 1 plus x squared over 2 factorial. Now we have to write down the next 4. Remember, write down means little to no work. Well, this is essentially little work because all we got to do is just keep following the pattern. We already know that the f primes of 0 are going to equal what value? 1, because it's e to the x. The derivative of e to the x is e to the x. When you plug in 0, you're going to get 1 every time. We just have to continue to increase until we get the next 4. So we're actually going all the way up to m sub 6. We're going all the way to m sub 6. So we're going all the way up to m sub 6. So let's start with m sub 3. That's going to be 1 plus x squared over 2 factorial plus x to the third over 3 factorial. Yes, it's a write down, little work. Okay, we are just following the pattern. There is a C and a D to this. So more than likely, we're going to be using this there. So I'm going to rewrite the first part, but now I'm going to add. Very good, and I keep going with m to the 5th order. Good. And of course, the last one. There we go. Now C says that we have to graph e to the x. And the first 4 polynomial approximations on the same set of axes. Discuss how the accuracy of the approximations is affected by the addition of the extra term. So let's take a look here. Pull up my calculator. So I'm going to make it a little bit bigger, but it's fine. E to the x. Take it back to a standard window. And actually, I'm going to zoom in just a little bit more. There's e to the x. And some other random line that I have somewhere. There it is. I'm going to plug in the first 4 approximations to y2, 3, 4, and 5. So I have the first 4 in there. Now, of course, I went ahead and did what 2 factorial, 3 factorial were, but for the last one, I did put in 4 factorial. It doesn't make a difference. I'm still going to get them. The factorial feature is found when you press math, go over to prob, P-R-O-B, and it's option 4. And we're going to take a look at it. Okay, now mine are going to graph the different colors. So please make sure that you're paying attention. I'm actually going to make this just a tad bit bigger. So then that way we can see it a little bit more effectively on our graph. Okay, and it's going to come quick. See what you see. Look at the comparisons here. Okay. Discuss how the accuracy of the approximation is affected by the addition of the extra term. So it's going to go red, black, pink, green. Take a look. Red, black, pink, green. Did everybody catch that? What happened as we increased terms? It's getting closer. So it's actually becoming more accurate. Yes. So the more terms we add, the more accurate it's getting. Just like as we add more terms, we are getting closer and closer, starting to converge to a particular value. Yes. So in that discussion, we would essentially say it's becoming more accurate with the more terms that we add. Okay. And then of course we would sketch a quick graph to support that. Exactly. Now it says copy and complete this table of values. Compare your results so where f of 1 equals to e. Whenever it says copy and complete in IB, you make sure that you do that. You copy over that table and you complete it. Do not lose points because you decide to fill in the table that's there. You copy it over. So then it says m sub n of 1. So that means we're plugging in each of these top values for n, and we're plugging in 1 for x into my equation, my series. Okay? So what is my series? My first one would be 2. Very good. Five over 2, which is, yep, 5 over 2. Let's do 2.5 because we are going to compare it with f of 1 equals e, and we're probably going to be a decimal. So we probably want that decimal approximation. Okay, so let's keep it going. I am going to go off video while I let you guys complete the rest of the table. But essentially you are following. Okay. So what did you get when n was 3? Or essentially when, yeah, n was 3. Okay, what's that? It shouldn't have been 1 over 6. It should not have been. So 2.6 repeating. Okay. What about when you plug in 4? Can you give me some more decimals after that?
I forgot the decimals after that. But it's like 2.708.
Okay. Did you do the same thing for 5?
I got 2.716.
Okay, couldn't been that then. Did you guys online? Did you guys do it when it was 4?
I rounded mine to 3 significant figures.
When I said give me some more decimals because we're kind of comparing it with f of 1 equals e.
I have 2.7083 repeating.
Okay, never mind, because it's increasing, not decreasing, my bad. All right, and then what you give for 6? So you were right, I take that. All right, what is e as a decimal? Plug it into your calculator, do e to the first power. So when we compare, and I'm pretty sure there was some decimals after this one. They're close, right? I mean, depending on what the next few decimals were after this 8 and this 6, it's, as we can see, as n increases, what's happening? Not of x, sorry. Of 1 is getting closer to e. Well, I mean, if we use in some other value for x, it would be probably e squared, or e to the 3rd, or e to the 4th. All right. So continuing along with that, the nth order Maclaurin polynomial approximation is the nth order polynomial the best fit for that particular curve. Okay, so when we find these particular numbered ordered approximations, we're trying to find the one that's the best fit. Since that nth order Maclaurin polynomial approximation is generated using the values of f and its derivatives at x equals 0, it will generally be the most accurate to where x is equal to 0. So that's why we usually, well, majority of the time, we only use it when x is equal to 0, not in some other number, okay? That's why, you know, in that particular one, you used 1. You're not going to use 2 or 3 or 4 like you asked. It's going to be more so 0 or 1.
Could it be -1?
Depends on the function. If it's a polynomial function, it could be. But, you know, once we get into e's and ln's and things like that, probably not. Now, the infinite Maclaurin series for f of x converges for any value of x such that the limit as n approaches infinity. So as n gets really large of a particular nth ordered Maclaurin approximation, it's going to equal f of x, whatever x is, as we've seen in the last two examples, right? When x was 1 for that fourth order Maclaurin series, it equaled exactly what f of 1 was, 1/3. It was very, very close. Same thing with the last example. The larger that n got, the closer we got to e. So the set of values of x for which the infinite Maclaurin series converges is called the interval of convergence. Now, there are particular intervals of convergence that you should be aware of, because if you're ever asked to determine which values of x would have your series converge, you probably should know these. We know an infinite series will only converge for values of x such that the terms of the series are getting smaller. So here are some, here are a few of them, and there are actually a few more that we'll see in a few pages. When you have 1 over 1 minus x, in general, this is what your series essentially simplifies out to be. The terms decrease in size when the terms decrease in size when the absolute value of x is less than 1. And indeed, the series is going to be convergent as the absolute value of x is less than 1. So essentially, if that x value that we plug in is smaller than 1, then the numbers are essentially getting smaller. So as we add smaller numbers, it's going to converge, okay? If x was anything larger than 1, as we square it, as we cube it, as we raise it to the 4th power, it's going to do nothing but continue to get bigger and bigger and bigger.
Yes.
Mm-hmm. Ln of 1 plus x, there's your series there. Okay, as you can see, my x's are being squared, cubed, raised to the 4th power, but they are being multiplied by 1/2, 1/4, 1/3, 1/4, and so on and so forth. It might seem like fractions would help the terms reduce in size. However, if x is again greater than 1, then the terms are going to continue to increase. If we use L'Hopital's rule for certain particular functions, it's not going to exist. So for the case of x equals -1, for this particular function, if I were to plug in -1, these will be the terms of my series. That's not going to converge. It's going to continue to get closer to essentially a larger negative number, okay? And it's kind of reasonable because since ln of 0 is undefined and we can't take, you know, the ln of 0, that makes sense why it wouldn't converge. So if that particular x value makes it undefined for the function, then no, it's not going to converge to a particular value. When x is equal to 1, it is going to converge. So when you're looking at the ln, it's going to be convergent on the interval from -1, not included, to 1, included. And lastly, you have e to the x. In this particular case, as you guys saw from before, this one does help us to converge. We just did an example with it. For any value of x that we pick, n factorial is always going to grow faster than any value to a particular exponent. So because n factorial grows a lot faster than x to the n power, it's going to reduce in size. And so the series is going to converge for all real values of x. So here, for the very first one, is only convergent for the interval when the absolute value is less than 1. For the ln, is only going to be convergent on that interval from -1 to 1. Only 1 is inclusive. And for e to the x, is going to converge for all values of x. So let's take a look at some examples. We're given the following Maclaurin series, and we're going to discuss the values for which we think that they're going to converge. What values of x we're going to think that they're going to converge. Cosine of x equal to 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over, I think that's 720, and so on and so forth. What values of x do you think it's going to converge for?
The n factorial is always going faster.
Exactly, because the factorials in the denominator are always going to grow faster than any x value raised to an exponent, then it is going to converge for all real numbers of x. What about b? Add in the note. Huh?
Would be the same thing.
It would be the same thing. Because it's getting smaller. So yes, for any value of x, it's going to converge as well. Same explanation. What about for c?
C and D are like the opposite.
-1 to 1.
They're getting bigger.
Oh wait, is that the absolute value?
Well, D would not be the absolute value
You said for d, it'll be the absolute value. For which values?
for
Anything
that's
less than 1.
bigger than 1. Well,
Anything between.
Less than 1?
Yeah.
It's going to be anything less than 1. Why not equal to 1?
because it wouldn't equal 1. Fraction of 1.
What happens if I plug in 1 for x?
Oh, 0.
It's-
So then it becomes undefined.
It's undefined, okay? It is undefined. Undefined. At x is equal to 1. So because of that, it can't equal 1. Because it just so happens that it is, then we're going to have some issues. What about for c, though? We skipped over c.
-1. X can be greater than -1. But
It has to be between the one.
Why?
Well.
I guess the other one.
It's tangent.
Yeah.
So
Where are they?
Remember, tangent, even arctangent, is sine over cosine. So you want to try to also like avoid the fact that, you know, you could potentially get something that's undefined, okay? We know that
At half pi.
at oh no, never mind, I'm taking y'all down the wrong path on that one, sorry.
Okay.
Also look at the first few terms that you have. Also look at the first few terms that you already have.
But what doesn't that include?
So this one would be the absolute value that's less than or equal to 1, okay? And so it's going to be all your values that are going to be greater than 0, but essentially in between 0 and 1, because you're taking the absolute value of them. Okay? And we can look at it like this. It's not going to be greater than 1, because if x is greater than 1, then those numbers are going to continue to get bigger and bigger, and they're going to diverge. Okay? However, if they're less than 1, then that means they're going to essentially, they're going to decrease, and they're going to converge to a particular number. It can equal 1 in this case, because at 1, our function isn't going to be undefined anywhere. Okay? And to be honest, if you look at all your trig functions, ln and e, it's not going to be any different from that. Okay? Or even like your polynomial functions that look like number 1. Rational functions. I'm going to skip over this example for right now and talk about some of the important Maclaurin series that you guys should know, because we can generate an infinite series representation for these other functions with composite functions. So e to the x, sine x, cosine x, arctangent, the ln of 1 plus x, and 1 plus x to the p power. So 2 important notes. Infinite series generated will only converge if the interval convergence of the original Maclaurin series is obeyed. Yeah. An infinite series generated is only itself a Maclaurin series if it's a polynomial. So 2 things to be aware of, which means essentially is that you're not going to be given any type of series that isn't a polynomial. Okay, like whether the Maclaurin series isn't a polynomial itself. So essentially it's not going to create something that's not a polynomial or a series of polynomials. And it only converges if the interval of convergence actually follows the Maclaurin series is actually a polynomial. So it's not like you're going to get anything that's like completely off the wall, nothing. It's essentially not a polynomial. Don't write this down, just kind of follow along with me because I am kind of running out of time here. We're going to use the Maclaurin series that we showed from earlier to find the Maclaurin series for this function, 1 over 2 minus x squared. We're going to write down the terms of the series up to x to the 6, okay? Up to x to the 6. So one thing you should recognize is that between the function that we're actually using and the function that we're actually given the Maclaurin series for, it's very similar. This is a few differences. What are the few differences? The denominator is 2 plus x for the original, but for this new one, it is 2 minus x squared. So we replace the plus with the minus, and we've actually increased the number of x's. So that essentially means is that we have a composite function here. If this one is my original function, what did I plug in for x to now have 1 over 2 minus x squared? Not a negative x, because if I plugged in a negative x, then it'd just be this. I plugged in a negative x squared. So that essentially means is that in order to write down my terms, I'm replacing every x in my formula with a negative x squared. So that means we're going to take our formula that was given to us, and we're going to replace that x with a negative x squared instead. Okay. And essentially from here, we are going to write down the series up to x to the 6. Okay. So now that means we need to follow through with the rest of the formula, simplify first, and then follow through with the rest of the formula. So when we do this, this becomes the sum. When k equals 0 to infinity of -1 to the k power, this essentially becomes negative power to a power u multiply. All right, and this can actually be simplified down even more because this is the same thing as saying -1 times x to the 2k. This -1 has the same base as this. And since we're multiplying, oh, actually, sorry. Yeah. My mistake. I was supposed to distribute over that k to both the negative and to the 2. Does everybody see that? I'll rewrite it like so. So when I apply that k, I should have applied it to the -1 and to the x squared. So now that I have a -1 to the k power and another -1 to the k power, and everything's being multiplied together, that can be rewritten how? It'll be -1 to the what power? The 2k, because remember when you multiply, you have the same basis you add, and then this becomes just x to the 2k over 2 to the k plus 1. Now, mind you, I'm trying to get to the point where I can write down the terms of my series, but I'm trying to simplify my expression first. -1 to the 2k power is what? -1 raised to the 2k. If I plug in 0 for k, or 1 for k, or 2 for k, or 3 for k, which is I am going to have to do, it's always going to be a positive number because a negative number raised to an even power is always positive. And the reason why it's going to be an even power is because it's 2 times a number. 2 times any number always makes it even. So I can remove that. So now my most simplified Maclaurin series is x to the 2k over 2 to the k plus 1. Now I can find my series up to x to the 6. It's in this most simplified form. Now, I did that so we wouldn't have all these long expressions that we would have to simplify later. By simplifying at the beginning, I save on simplifying at the end. So now that I have that, now I can plug in 0, I can plug in 1, I can plug in 2. So if I plug in 0 into the series, what do I get for k? I'm going to get 1 over 2. Okay. I still got to keep going. This is when k is equal to 0. What do I get when k is equal to 1?
X squared over
4, because it becomes 2 to the 2nd. So then that's 4. I got to keep going because I'm not at x to the 6th yet.
You are.
No, I'm not.
No,
I'm at x to the 2nd.
You're x to the 4.
Now I'm at x to the 4 because I have x to the 4th over.
8.
Very good.
Here we are.
X to 6.
I'm at x to the 6th over.
4, 16.
And there is the term of my series, the terms of my series up to x to the 6th. Of course, it would keep going after this because it is a series, but we just want the ones up to the 6th power. We're going to use Maclaurin series for 1 over 1 minus x. And we're going to see if we can write down all the terms before time is up. What's the difference between what I'm given versus what I'm trying to find?
If you plug in 1/2 into, no, 2x, yeah.
I'm going to plug in a
2x.
I'm going to plug in a 2x for x. So then that means in my formula, I'm going to have a 2x to the k power. So that means for this particular expansion for 1 over 1 minus x, which is, I know we had this down somewhere else.
My time's up. Dang. All right, I'm gonna finish this video at home for you guys, but I'll finish this up. Make sure you watch, y'all add on the extra one. Only after you watch those videos, then attempt the homework.
Okay.